Hello everybody, in this video we will be discussing how to find the linearization of some curve at a point. Ultimately, we're going to use this linear approximation formula that we have over here to find the equation of a tangent line that passes through our curve at a specified point. We have this example here that tells us to find the linearization of the logarithmic curve f of x equals log of x, and we want to find the linearization at the point x equals 0.5. We're trying to find the equation of a line, and so over here I have written point-slope form for the equation of a line. How is this relevant to what we're doing? Is because the linear approximation formula is really just point-slope form in disguise. And so we know that point-slope form requires two things. It requires a point and it requires a slope. The point goes here and here, the x and the y values, while the slope goes here. I also took the liberty of color coding it for us down here. Now, if we go and kind of examine the rule that we have for a linear approximation, realize that everything takes the same form. So instead of my y variable, I have my function notation, which we're calling L of x. Instead of y1, which represents the y-coordinate of my point, I have f of a, which also represents the y value of my point, if we're talking about the point that has the x value equal to a. I have f prime of a. F prime of a represents the derivative at my point, and think of what that means here. So we know that the derivative is a function that tells us the slope at any point in time. So if I know that the slope goes here, hopefully it makes sense that the derivative evaluated at that point will give us the slope at that point, and that's why we put it in that position. And then we multiply that times x times whatever the x value at that point is. We're talking about the point a comma f of a, and so the x value will be a. Notice that if we add this f of a to both sides, then we get our basic rule for our formula for the linear approximation. And we see here that our point happens to be a comma f of a, and our slope happens to be f prime of a. And so just like with point-slope form, all I need are two little things. I need to know what's my point and what's my slope. In this example that we have over here, I'm seeing that they're giving me the point x equals 0.5, but that's only half of my point. I have the x value. What's the y value? That's easy to find. We'll just plug in that x value to find the corresponding y. And so I see that my y value is log of 0.5. That tells me my point is 0.5 comma log of 0.5, which we can worry about plugging into the calculator later. Next, we need a slope. We know that in calculus, when we're dealing with the slope, that usually comes from the derivative. So I need to take the derivative of my logarithmic function here. The derivative of this logarithmic function will give me a new function, aka the derivative, but this function will represent the slope at every single point in time on the function, so we can use it to find the slope specifically when x is equal to 0.5. If f of x equals log of x, the derivative of f is going to represent the derivative of log of x, which happens to be 1 over x times ln of 10. So here's our derivative. Realize this represents a function that I can plug in any value to find the slope of my original function at any point. And so I'm going to plug in my point that they asked me to plug in. I'm going to plug in 0.5. And I see that I get 1 over 0.5 ln of 10. This all here represents the slope of my tangent line at that point. And so 0.5, realize that the logarithmic function crosses the x-axis at 1, so 0.5 must be here. I see we have this point here is what we're dealing with, and so we just found the slope of the tangent line that would be at that point. I see it's about that, it's looking like. I I found the slope of that line. I found a point on that line. So I have a point and the slope of that line. I have enough information to go and write the equation of this line in point slope form. Or, as we like to say, we want to write the linear approximation of this line. So I'm going to plug everything in now. I have L of x. L of x is equal to whatever f prime of a is equal to, which we see happens to equal this. One over 0.5 ln of 10 times x minus a, which is x minus 0.5 because a was our 0.5 value, plus f of a, which is what we got up here, log of 0.5. And there we have it. There's our linear approximation.